Imagine stepping into a booth, pressing a button, and instantly appearing on the other side of the world. The idea of teleportation has always been a fascinating one, capturing the human imagination with its promise of instant travel and the ability to transcend physical boundaries. This is the tantalizing promise of teleportation, a concept that has captivated our imaginations for decades. The allure of being able to move from one place to another in the blink of an eye is irresistible. From the transporter beams of Star Trek, which have become iconic symbols of futuristic travel, to the magical apparitions in Harry Potter, where wizards and witches can disappear and reappear at will, teleportation has been a staple of science fiction and fantasy. These stories fuel our dreams and inspire us to think beyond the limits of our current technology. But what if this fantastical idea wasn't so far-fetched after all? What if the science fiction of today could become the science fact of tomorrow? What if the ability to travel instantaneously wasn't just the stuff of fiction, but a potential reality waiting to be unlocked? The implications of such a technology would be profound, changing the way we live, work, and interact with the world. In the realm of science, teleportation is no longer confined to the realms of imagination. Researchers are making strides in understanding the principles that could one day make teleportation possible. Scientists are exploring the fundamental laws of physics, pushing the boundaries of what we know about the universe, delving into the strange and counterintuitive world of quantum mechanics, where particles can exist in multiple states at once and be entangled across vast distances. To understand the possibilities and limitations of teleportation. Quantum teleportation, a process by which information about the state of a particle is transmitted from one location to another, is already a reality in the lab. While we may not be beaming ourselves across continents just yet, the progress being made is exciting and opens up new avenues for exploration. The journey of scientific exploration is leading us down a path that could revolutionize our understanding of space, time, and the very nature of reality itself. Imagine a world where distance is no longer a barrier, where we can connect with anyone, anywhere instantly. The very fabric of reality is being examined and redefined. And with each discovery, we move closer to turning the dream of teleportation into a tangible reality. The future holds endless possibilities, and teleportation could be one of the most transformative technologies we ever develop. At its core, teleportation is about transferring information, the information that defines an object's structure and state from one location to another. This concept, while seemingly futuristic, is grounded in the principles of physics and information theory. Imagine being able to send not just data, but the very essence of an object across vast distances in the blink of an eye. Instead of physically moving an object through space, teleportation relies on the idea of deconstructing an object at its origin point. This involves breaking down the object into its fundamental components, analyzing its structure at a microscopic level, and encoding this information into a transmittable format. The process is akin to taking apart a complex machine, documenting every single piece and then sending this blueprint to another location. Transmitting the information that describes it is the next crucial step. This information, which includes every detail about the object's physical and chemical properties, is sent through a medium, much like how data is transmitted over the internet. The challenge lies in ensuring that this data is transmitted accurately and without loss, as even the smallest error could result in a flawed reconstruction, and then reconstructing an exact replica at the destination point. This reconstruction process would require advanced technology capable of interpreting the transmitted data and reassembling the object with perfect precision. It's a bit like receiving a complex set of instructions and using them to build an exact copy of the original object down to the last atom. This might sound like something out of a science fiction novel, but the seeds of this concept are rooted in the bizarre world of quantum mechanics. Quantum mechanics, with its counterintuitive principles, provides a theoretical foundation for teleportation. It challenges our classical intuitions and opens up possibilities that seem impossible in the macroscopic world. Quantum mechanics, the branch of physics that governs the behavior of matter at the atomic and subatomic levels, introduces us to phenomena that challenge our classical intuitions about the universe. At these tiny scales, particles behave in ways that defy common sense, exhibiting properties like superposition and entanglement that have no parallel in our everyday experiences. One such phenomenon, known as quantum entanglement, plays a crucial role in the theoretical framework of teleportation. Entanglement is a mysterious connection between particles that allows them to share information instantaneously, regardless of the distance separating them. This phenomenon has been experimentally verified and is a cornerstone of quantum theory. Quantum entanglement describes a strange connection that can exist between two particles, no matter how far apart they are. When particles become entangled, their properties become linked in such a way that the state of one particle is directly related to the state of the other. This connection persists even if the particles are light years apart. These entangled particles share a fate. A measurement performed on one instantly affects the state of the other, even if they are separated by vast distances. This instantaneous change occurs faster than the speed of light, defying the classical notion that information cannot travel faster than light. This peculiar property of entanglement is what makes it a key element in the concept of teleportation, as it allows for the transfer of information in a way that transcends traditional physical limitations. Albert Einstein famously referred to quantum entanglement as spooky action at a distance because it seemed to violate the principle of locality, the idea that an object can only be influenced by its immediate surroundings. In classical physics, this principle is fundamental. It means that for one object to affect another, they must be in close proximity or connected by some form of signal that travels through space. How could two particles separated by light years communicate with each other instantaneously? This phenomenon defies our everyday understanding of space and time. This question puzzled even the greatest minds of the 20th century. Scientists like Niels Bohr and Erwin Schrödinger debated the implications of quantum entanglement, trying to reconcile it with the known laws of physics. Despite its strangeness, quantum entanglement has been experimentally confirmed time and time again. Experiments conducted over the decades have consistently shown that entangled particles behave in ways that classical physics cannot explain. It is this spooky action that forms the bedrock of quantum teleportation. Quantum teleportation relies on the entanglement of particles to transfer information instantaneously, bypassing the limitations of classical communication. By entangling particles at both the sending and receiving locations, scientists theorize that it might be possible to transfer information, and potentially even matter, between them. This process involves creating a pair of entangled particles, sending one to the destination, and then using the entangled state to transmit information. However, teleporting something as complex as a human being presents a whole new level of complexity. The human body is not just a collection of atoms, it is an incredibly intricate system with countless interactions and dependencies. The human body is composed of trillions of atoms, each with its own unique quantum state. Mapping the quantum state of every single atom in a human body is an enormous challenge, requiring technology far beyond our current capabilities. To teleport a person, we would need to map the quantum state of every single atom in their body, transmit that information, and then perfectly reconstruct the person at the destination. This process would need to be incredibly precise, as even the smallest error could result in catastrophic consequences, and then perfectly reconstruct the person at the destination. The idea of teleportation, as seen in science fiction, remains a distant dream. But the study of quantum entanglement continues to push the boundaries of our understanding, opening up new possibilities for the future. As we delve deeper into the mysteries of quantum mechanics, who knows what other spooky phenomena we might uncover? The journey of discovery is just beginning, and the potential applications of quantum entanglement are vast and exciting. From secure communication systems to advanced computing, the principles of quantum entanglement could revolutionize technology in ways we can only imagine. The future of quantum research holds promise and intrigue as we continue to explore the fundamental nature of reality itself. Section 4. Teleportation breakthroughs from photons to atoms. While teleporting humans might still be a distant dream, scientists have made remarkable progress in teleporting smaller objects. In 1997, researchers at the University of Innsbruck in Austria successfully teleported the quantum state of a photon, a particle of light, over a distance of several meters. This groundbreaking experiment demonstrated that it is possible to transfer quantum information from one particle to another without physically moving the particle itself. Since then, scientists have gone on to teleport the quantum states of atoms and even molecules over increasingly longer distances. In 2017, a team of Chinese scientists reported successfully teleporting photons from Earth to a satellite orbiting over 500 kilometers away. This achievement marked a significant milestone in the field of quantum teleportation, demonstrating the potential for long-distance quantum communication. Section 5. The challenges of teleportation, matter and energy. While the teleportation of quantum states is a remarkable feat, it's important to distinguish this from the teleportation of matter itself. Teleporting the quantum state of a particle doesn't mean we've physically moved the particle, it simply means we've transferred the information that defines its state. Teleporting matter, on the other hand, would require converting an object into energy, transmitting that energy to another location, and then converting it back into matter. This process, while theoretically possible according to Einstein's famous equation E=mc², presents a host of technological and ethical challenges. The amount of energy required to convert even a small object into pure energy is astronomical. Furthermore, the process of converting matter to energy and back again would need to be perfectly controlled to ensure that the reconstructed object is an exact replica of the original.